Hi guys, just another review of the classification of matter, and this PowerPoint has been updated compared to what we had talked about in class, so this should be helpful for reminding you of what you need to know and be able to understand. So when we classify matter, we can break it down into two major categories. Our pure substances, which include elements and compounds. I'm going to briefly today remind you that element symbols are usually the periodic table symbol, but there are times that we have to use special symbols. Also, we're going to talk about compounds with some examples. There are 4 common compounds that you're going to need to have memorized their formulas, and we'll talk about that in a bit. And 2 types of mixtures that we're going to talk about. You may be asked on a test to replicate this schematic diagram, breaking down the classification of matter into pure substances and mixtures, telling me that pure substances include elements and compounds, and giving me a couple examples of each, and then telling me that mixtures can be either homogeneous or heterogeneous, and then giving me several examples of each. So talking about elements first. Elements are made of only one kind of atom, and an atom is the smallest unit. I'm sorry, I had an itchy back. I'm not really sure how that may be coming across. I was just unconsciously scratching it. Oh well. Let me start over. Talking about elements. When we look at element symbols, typically if the element symbol on the periodic table, for example, zinc, the symbol on the periodic table says Zn. And most elements have their chemical formula, when we describe them in reactions and formulas, is just the element symbol. But there are 7 elements that are called diatomic, and I will remind you that they either end in gen, G-E-N, or this is supposed to be an I, or I-N-E. So there's a saying that diatomic elements are genuine. And these diatomic elements include, I have to look at the periodic table so I get them in the right order, nitrogen, which his formula is N2, oxygen, which is O2, fluorine, which is F2, hydrogen, which is H2. Again, on the periodic table I gave you, the hydrogen is located in 2 spots. One spot is above the fluorine. Beneath the fluorine we have chlorine, which is Cl2, bromine, which is Br2, and iodine, which is I2. There are 2 polyatomic elements. One is sulfur. The formula for sulfur is S8, most commonly. And the other is phosphorus, and the formula for phosphorus is P4. So these are what I like to consider the 9. The 9. Because these 9 elements have extra subscripts in their formulas when we're expressing the element formulas. All of the other elements just have the element symbol. So these are the 9. You should make sure that you have these on your periodic table. They should have been listed had you done the periodic table activity already. Okay? Here are some examples of elements. We have diamond carbon and diamond graphite. Oh, I really screwed that up. Let me start that over. These are both carbon. This is diamond, this is graphite. Very different properties. We talked about this in class, and it all has to do with how the atoms are arranged. Whoops. So each of these carbon atoms is attached to 4 other carbon atoms in a very rigid strong network of covalent bonding. In this structure with graphite, which is very, very soft, we have these carbon atoms in these little hexagons, and they form sheets. And those sheets are all stacked like a bunch of pieces of paper. And if you have ever walked across the floor and stepped on a magazine and ended up slipping, you know how slippery that can be because those sheets of paper and that slippery paper just slide right past one another. I've fallen a couple times doing that. So, same element, carbon, two very different forms of it. Here's some copper, here's some iron, and here are different forms of sulfur. Compounds are made from atoms of two or more elements chemically bonded. The smallest unit of a compound is typically the molecule. Compounds cannot be separated using physical means. They can be separated using chemical means. For example, if you take water, regular old H2O, you can run electricity through it. That is a lightning bolt. It's not real in terms of a symbol that's used in chemistry, but I put it there because I like it. So I'm running electricity through it. Lightning bolt, that was a horrible sound, can be broken down into the elements hydrogen and oxygen. All right, this is a chemical process. But compounds can't be broken down by physical means. Some examples include carbon dioxide, CO2, iron 3 oxide, which the formula is Fe2O3, copper 2 carbonate, which has a formula CuCO3, and sulfur dioxide is SO2. We will learn more about these chemical formulas and writing in a future unit. This is an example of a water molecule, and this is called a ball and stick model. Here is a beautiful copper mineralization, copper compound, copper carbonate. This is some sulfur dioxide, a haze over a city, and this is some iron oxide, which is a form of rust. So behind here we have some iron. It oxidizes with the oxygen and forms rust. Now there are 4 common compounds in chemistry that if you're reading any chemistry book, they assume that you know these, and they include water, hydrogen peroxide, which all of you are familiar with these two, is what I was trying to say. And also another common one that we speak of is ammonia. It has a formula of NH3, and methane has a formula of CH4. So you should memorize these, commit these to memory, because they frequently will surface in chemistry problems. And any chemistry program will assume that you know what they are. So this is a model of water. This is just a reminder that when we talked about density of substances, we said that solids consist of atoms very, very close together in a very ordered arrangement. They just wiggle and jiggle and vibrate in place. And liquids are a little bit further apart, still pretty close together, not showing any pattern, and they can move freely, also wiggling and jiggling. And then a gas is very far apart, wiggling and jiggling pretty violently, and they can move all over the place. So what we said is that in most substances, the solid form is the most dense form of the matter. So I want to remind you that with water, it is a unique substance in this universe. It is a substance that actually, when it becomes a solid, becomes less dense. You can see the solid form here is arranged, and the amount of space between each molecules is significantly more compared to the liquid version in this molecular drawing, this model. So a unique substance, it results in water floating, and there isn't another substance like it in the universe. When we're looking at models, we can use the ball and stick model, and that is commonly used. Another form that we see frequently is called a space fill model, and I think this model is just kind of cute, cartoony model, and sometimes I like to do things like that. All right, So now looking at mixtures. A mixture will contain more than one substance, and one of the keys with a mixture is that it can be physically separated. They're combined physically, so they can be physically separated. And we have two types of mixtures, homogeneous mixtures and heterogeneous mixtures. Homogeneous mixtures are also called solutions. A homogeneous mixture has the same uniform appearance and composition throughout. And one thing to note that is if you're looking at a solution, a homogeneous mixture, it will remain uniform in composition even at the microscopic level. So the contents are so uniformly distributed that even if you looked at it microscopically, you wouldn't be able to separate one component from the next. They can still be separated by physical means. For example, a saltwater solution is a homogeneous mixture, and all we would need to do is evaporate off the water to get the salt back through that evaporation and crystallization process. I am not really sure why that happened. All right. The point of my next slide is to remind you that another name for homogeneous mixtures is solutions. Another name for homogeneous mixtures is solutions. Homogeneous mixtures are solutions. Doesn't matter if the homogeneous mixture is a solid, like a metal alloy, such as brass, or a gas, like the air that we breathe. Every time we inhale and exhale, you can not see anything, so I am inhaling and exhaling two different homogeneous mixtures. I inhale primarily nitrogen, a small amount of carbon dioxide, and oxygen, and I exhale a higher amount of carbon dioxide. So the mixtures are different in composition. So two different mixtures happening right here, just as I'm sitting here breathing, and they're uniform in composition, and I am inhaling air. It is a solution, a gaseous solution. Exhaling my bodily exhalations, which is my breath, I guess. I don't know what else to call it, but also a solution. And here we have some air and some lipstick and some water-based solutions and some brass. So looking at brass at the molecular level, so brass is zinc and copper atoms. Copper looks like this, zinc looks like this. Copper at the atomic level would contain all copper atoms. When you look at brass, you see that there are copper atoms and zinc atoms. So the resulting, the end mixture looks very, very different than the original ones. Now, homogeneous mixtures are solutions. This is a solution. Some other solutions include different combinations. So if the solute is sugar and the solvent is water, you have a solution type, it's solid liquid. So the sugar dissolves in the water. An example is maple tree sap. Pop, I grew up calling it pop. Many of you might call it soda, but we're talking about regular old soda pop here. Coke, Coca-Cola, Fanta, Mountain Dew, whatever it is. It contains dissolved carbon dioxide, and that dissolved carbon dioxide gas is soluble in the water. So we have a gas liquid solution type. Windshield washer fluid contains alcohol and water, so that is a liquid-liquid type of solution. And another liquid-liquid type of solution is vinegar. It contains acetic acid, which is a liquid, and water, which is a liquid. So these are some more examples of solutions in discussing homogeneous mixtures. All right. Heterogeneous mixtures are made of different substances that remain physically separate. They are not uniform in composition, as you can see right here. Now a little note. There are some heterogeneous mixtures that may appear homogeneous to the eye. For example, if you donated blood and you looked at the blood in the bag as is coming out of your arm, it all looks to be homogeneous. But if you look at it under a microscope, you will see the individual components. We have platelets and red blood cells and white blood cells and other components in the blood. Milk fat is another one, or milk in general. You can see protein, you can see fat globules, water. So milk is actually a heterogeneous mixture. Again, microscopically, you can see distinct components that remain physically separate. Here are some more heterogeneous mixtures. Oil and water. The oil is less dense than the water. Here we have some sulfur and some iron filings, some birdseed. This is bauxite, it is a rock, and this is layered smog above a city. Here we have some colored food coloring in water. And here are some more granite and human blood demonstrating heterogeneous mixtures. With the naked eye, am I being inappropriate if I'm watching this with my naked eyes? I don't think so. You can see the individual components. You can see it microscopically as well. With the human blood, again, when you look at it with the nude eye, it all looks uniform in composition, but at the microscopic level, it does have individual components. However, copper 2 sulfate is a homogeneous mixture called a solution. Microscopically, it's not going to look any different. So if we can summarize our classification of matter and into the categories we talked about, we have pure substances, which contain elements and compounds, and we have mixtures. If the pure substance contains atoms of only one kind, it's an element. If it contains molecules that have more than one kind of atom, it's a compound. If a mixture is uniform in composition, like table sugar mixed in water or water mixed with salt, it is a homogeneous mixture. This isn't really the best model to represent that, because when I'm looking at this model, I see these individual components, so I'm not so happy with this model. But if you can see some individual components, you can see that there's a distinct zone here where different parts of the mixture are in this model. So this is just another modeling showing different states of matter, liquid water molecules very close together. And when you run electricity through water, you break it down into hydrogen molecules. Remember, it's diatomic, and oxygen molecules. They're both gases, lots of space between them. Again, looking at models of matter, these would all be gases. All of these atoms are the same, as are these. So these are both elements. This would be a diatomic element. Here, all of these molecules are the same. Here we have some elements and molecules all in the same space, also gaseous, lots of space in between these components, but that would be a mixture. And one more final breakdown. All matter can be broken down into pure substances and mixtures. Elements contain atoms of only one kind. You can see this model. The matter would be a solid, organized, very close together. And compounds, this is water molecules, liquid, very close together. A homogeneous mixture would include brass. This is a solid. You can see that the atoms are very close together. They're orderly arranged, but there are atoms of two different types. And heterogeneous, you can see those components within the watery sort of matrix. So that summarizes the review of how matter can be broken down, and I wish you the best of luck when you are finally assessed on this. And that's the end of this presentation. Thank you.